Hello and welcome to today's webinar. I'm Stu Borman of CNE News and I will be moderating today's event. This webinar on unleashing the power of thermogravimetric analysis, TGA or STA, by coupling to FTIR, MS, and GCMS for characterization of evolved gases is being sponsored by Netsch Group. CNE News works with sponsors to identify topics of interest and value to CNE News' audience, consistent with our mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please use the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the webinar by asking questions at any time during the presentation through the Q&A box on your screen. The Q&A session is at the end of the presentation. As your moderator, I will be posing as many of your questions as time permits. CNE News does not endorse any company products or services mentioned in the webinars, and each webinar will be archived at CNE News Online after the live webcast. As mentioned, today's presentation is sponsored by Netsch Group, a mid-sized, family-owned German machinery and instrumentation manufacturer. Netsch's Analyzing and Testing business unit develops, produces, and markets thermoanalytical instruments for testing physical and chemical properties of metals, glass, ceramics, plastics, and other materials. The instruments are used for R&D and quality control worldwide in a diverse range of applications spanning from the development of fuel cells to the characterization of pharmaceuticals, and from failure analysis of polymer parts to the optimization of building insulation. Today's speaker is Jan Hans. Jan earned a Dr. Rerum Naturalium degree, the equivalent to a PhD, in chemistry. He has more than 15 years' experience in thermal analysis. He is a faculty member in a solid-state group at the University of Augsburg, and since 2012, he has been head of the application laboratory at Netsch. Jan, please go ahead.
Okay, Stu, thank you. So, hello everybody. I hope you have also the same weather like we have it here. So it's nowadays 20 degrees C, and I enjoy the weather, and now I hope we... So, okay. So I heard that something was a problem with hearing me, but I hope now everybody is hearing me. And due to the nice introduction of Stu, I can skip the first slices. There, the
Hello and welcome to today's webinar. I'm Stu Borman of CNE News, and I will be moderating today's event. This webinar on unleashing the power of thermogravimetric analysis, TGA or STA, by coupling to FTIR, MS, and GCMS for characterization of evolved gases is being sponsored by Netch Group. CNE News works with sponsors to identify topics of interest and value to CNE News' audience, consistent with our mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please use the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the webinar by asking questions at any time during the presentation through the Q&A box on your screen. The Q&A session is at the end of the presentation. As your moderator, I will be posing as many of your questions as time permits. CNE News does not endorse any company products or services mentioned in the webinars, and each webinar will be archived at CNE News Online after the live webcast. As mentioned, today's presentation is sponsored by Netch Group, a mid-sized family-owned German machinery and instrumentation manufacturer. Netch's Analyzing and Testing business unit develops, produces, and markets thermoanalytical instruments for testing physical and chemical properties of metals, glass, ceramics, plastics, and other materials. The instruments are used for R&D and quality control worldwide in a diverse range of applications spanning from the development of fuel cells to the characterization of pharmaceuticals, and from failure analysis of polymer parts to the optimization of building insulation. Today's speaker is Jan Hans. Jan earned a Dr. Rerum Naturalium degree, the equivalent to a PhD, in chemistry. He has more than 15 years' experience in thermal analysis. He is a faculty member in a solid-state group at the University of Augsburg, and since 2012, he has been head of the application laboratory at Netch. Jan, please go ahead.
Okay, Stu, thank you. So, hello everybody. I hope you have also the same weather like we have it here. So it's nowadays 20 degrees C, and I enjoy the weather, and now I hope we... So, okay. So I heard that something was a problem with hearing me, but I hope now everybody is hearing me. And due to the nice introduction of Stu, I can skip the first slices. There, for sure, the title, and then well, what we are talking today, and also some slices about Netch companies. And as Stu said, we are a family group company, and here some information about the three product lines which we have at Netch. But today we want to talk about the fascination of gas analysis. So the next picture here, what you see is a TGA curve. I think everybody who made TGA in his life has seen it. But the question is always, what happens, what reactions happen, what gases are evolved if we have a decomposition, or also if we have mass increases, there are changes in the gas phase. And we at Netch offer a lot of products. So we are offering TGA and STAs with MS, with FTIR, with GCMS, and also you can couple two instruments at the same time if it's necessary. So this is no problem. Here you have a small overview of the possibilities, coupling of evolved gas analyzers to STAs or TGAs, but for sure you can also couple these analyzers to other instruments. So even a dilatometer, it's possible to couple a gas analyzer. So I first want to talk to FTIR. I think FTIR is one of the oldest one, and from the history of my talk, FTIR, then mass spectroscopies and GCMS, I think this is the right way to start. With FTIR, sorry, we have an interaction of the infrared radiation with molecules, here in the example of water, and you see the vibrations, and the energy is taken out. You can later see after Fourier transformation in your FTIR spectrometer, and this would be, for example, the resulting absorption spectrum of water. For sure, this is a gas phase spectra, because in the liquid phase you have much more broader absorptions, but we are talking today of the gas phase. FTIR in principle gives you information of the absorption, and you know it from the organics that every functional group has different absorption regions where they do absorb it, and it's well known in the organic chemistry. So when I started to study chemistry in the beginning in organic chemistry, we used an FTIR. But also for inorganic gases, you have typical spectra, the water spectrum, the carbon dioxide, the carbon monoxide, HCl, and things like this are typical spectra that you can identify them. One disadvantage of FTIR spectroscopy is that you can't detect homonuclear molecules like H2, O2, N2, and for sure the noble gases, because you need a dipole-dipole change. And compared to mass spectroscopy, it has a smaller linear range for quantification. Quantification is possible, but the linear range is smaller with the FTIR. Here you see one of the possibilities which we have on the right side, a TGA, our TG209 F1 Libra, and coupled with a Tensor 2 from the company Bruker. In the middle there's an external FTIR measuring cell that you can use the internal measuring compartment for doing other measurements. If you do not want to have an externally, it's also possible to use it internally, but sometimes it's easier if you have both possibilities. Another way of coupling, here's the schematic part. You see on the right side the TGA measuring cell, the furnace, then the gas is going out, transferred via heated transfer line to the FTIR gas cell. This has a small inner volume that you do not have a big dilution and that you do not have broad signals, so small volume, long path lengths or relatively long path lengths to the volume, and then at the end the outlet. So typical if you want to couple a TGA or an STA to an FTIR. Since now 4 years, we are also possible to couple a small FTIR spectrometer directly to the furnace. This is seen here. So we have the furnace of the STA in the middle, where you can see schematically is a sample in the furnace. Then we have a short part, transfer part to the FTIR measuring cell. It's heated. You can heat it controlled or uncontrolled, and the measuring cell is also controlled, and then the outlet is going to the waste or to an out-of-vac system if you want to evacuate and refill the system in the beginning that you have best gas atmospheres. This is called our so-called Persis coupling. Here's an example, a sample of soft PVC, where you can see in the green line the TGA curve with 2 mass loss steps in the beginning, and then after switching to air at around about 850 degrees C is the third one. This is the green curve. The black curve is a DTA curve, where you see the 3 mass loss regions, and in blue the FTIR Gram-Schmidt. There you see the first and the last really good, and the middle peak is not seeing so good, but it's still there. And you can also show this in combination with the FTIR, that you have the TG curve with a three-dimensional FTIR spectra, because every spectra is measuring after, let's say, around about 20 seconds, and you can clearly see it and have a nice way for the presentation. If you take, for example, the measured spectra at 320 degrees C, you can go to the library, and in the library it's easy to identify the DOP, the Dioktyvphthalate, which is in the sample in for softening. Nowadays it's not allowed anymore, but in former days it was often used. And you see the evolution of the hydrogen chloride. For going to another example, so I took a mineral, so an aluminium silicate, the topaz, and we measured this with an STA. And here in the STA you have in green at the top with a dotted line you have the DTG curve, then down the green line from the TG curve, the blue the DSC, and in black again the Gram-Schmidt curve. And for sure you can also show again a 3D plot, but you can also follow absorption spectra that you over the whole region, and what you can see is that we have an evolution of hydrogen fluoride and silicon fluoride. So showing us now here in a three-dimensional way, so the hydrogen fluoride in red and the silicon fluoride in pink, and the TG curve and the DTG curve still in green. So this is also possible with the software. It's no problem to follow traces or to make this three-dimensional part. This is what I wanted to show you for FTIR. If we go now to mass spectroscopy, and sorry, I started in 1999 with mass spectroscopy and in 2003 with FTIR, so mass spectroscopy is the analytical part which I use more, and you know sometimes the first things which you use more are the famous things for you and the most important, so we'll talk a little bit more about mass spectroscopy. Mass spectroscopy, in the mass spectrometer you must make a pressure reduction, and you can do it with an interface, because in the thermal balance you are in the normal pressure range and you have to go down to 10⁻⁵ millibars in this region. When you are in the mass spectrometer, then you have your evolved gas inlet, your ion source, and your electron beam, and the electron beam makes the molecules to ions, and then the ions go to here in this part to a quadrupole, to the rods, to the detector. And I have been 13 years at university and teaching always people about things like mass spectroscopy and recognizing that people have as carbon dioxide always a mass number 44 in their mind, but not other mass numbers. So I want now to show you which mass numbers you can observe with a mass spectrometer for carbon dioxide. For sure, you go with an electron beam, put an electron out, you have charge 44 with +1, and then you see mass 44. If you take out 2 electrons, then you have mass 44 with 2+ as an ion, and this is detected in the mass spectrometer with 22. And you see the mass number 22 also for carbon dioxide. But you also have fragmentation. And here I didn't put the charge on it, because charge could be on different molecules. So you have with fragmentation the carbon monoxide, which has mass number 28, and the O with mass number 16. And you can also make the fragmentation that you see the mass number 12. So this is all possible. But what we shouldn't forget is that we also have isotopes. And if we look in a book for chemistry with isotopes, we see that we have round about 99% carbon-12 and round about 1% carbon-13. And with the oxygen, we have the oxygen isotope 16 and 17 and 18. And now you can make all the calculations. And I only made the calculations for the total molecule. So with mass number 44, this is the highest intensities. The mass number 45 is a factor of 84 lower, 46 round about 250 lower, and so on, like you see it in the numbers. And the question is, could I detect this with a mass spectrometer? And for sure I said yes, because I measured with one of my instruments the evolution of carbon dioxide from baking powder. And what you see here is 45 is factor 83. I calculated 84. The 46 was 244. I calculated 249. And also the 21,360 also fits very good. And also that my other mass numbers like 48, I can see it. With 49, I would say maybe this was not good enough, my instrument, or it was too broad. But if you see, remember that the factor was more than 2 millions. So this is really small amounts of evolved gases. We have, with the mass spec, two possibilities. We have the coupling of quadrupole mass spectrometer power for 3D IA loss via a transfer line where we make the pressure reduction, or with a skimmer. And on the next slide you see the schematics of these two instruments. So on the left side we have the IA loss coupling, where we had in green the heated adapter where the transfer line is attached, and you can also put the transfer line around to the bottom of the green part, that it is in the hot zone, that you have less problems with condensation. The adapter can be heated to 300 degrees C, and transfer line and inlet into the mass spectrum at the same temperature, so all could be heated to 300 degrees C, that you have less condensation. And the mass spectrometer only needs small amount of your gas, so we have an outlet on the side where you can attach another gas analyzer if you want, or only go to the waste. This is a normal coupling which everybody has, and the easiest way to couple a mass spectrometer to any other instrument which you want. On the right side you see our skimmer interface. The skimmer interface is a two-stage pressure reduction into the mass spectrometer, where we have the sample at normal pressure going through a small orifice into the low pressure region, millibar region, and in the second step via the skimmer orifice into the high vacuum. The big advantage of this interface is that you nearly have no condensation problems. Even with the IA loss coupling with the 300 degrees C, you know that there are substances which would condense at 300 degrees C. Here with our skimmer interface, the inlet into the mass spectrometer has nearly the same temperature like the sample, so there's no problem with condensation. For sure, what you always can have is problems of interactions with the materials. So with the skimmer system here, which is shown, we have the possibility of aluminum oxide interface or of graphite interface. And with aluminum oxide you can go up to 1450 degrees C. With the graphite interface you can go to 2000 degrees C, but with graphite for sure only under inert conditions. So here are some examples. And one big problem is always if you make your own coupling of an instrument, you must be aware whether you have a cold spot, yes or no. Here are shown 3 solvents, decan in green, dodecan in red, and heptadecane in blue. They have boiling points from 174 up to 302 degrees C. And with the dotted lines or dashed lines, you see the total ion current in the mass spectrometer. And you see that it's with the green maybe comparable, but with the red, the time shift and temperature shift, and with the heptadecane, you nearly see the total increasing. This was an instrument where I have put in for sure a cold spot, and I have done it for presentations that people can see what happens if you have from the outlet of the furnace to the heated transfer line a cold spot, and this makes problems. For sure you can also have these kind of problems not due to cold spots. You can also have it due to chromatography if you have a long transfer path and wall reactions, but this in this case was a real cold spot. And I do the same, have done the same measurement with the same mass spectrometer and the same settings of the mass spectrometer with an STA and the normal heated adapter, and you can see that there's a small difference in time compared to the maximum of the tick and the minimum of the TGA curve. This is around about half a minute. And for sure, if you have evolution and you have a gas path, the reaction in the mass spectrometer or the detection must be a little bit later. So everything fine, and it goes fine down, so no problem. So with the ILOS 3 for 3D ILOS and STA with a heated adapter, so no problem with things boiling point 302 degrees C. For sure, if you go higher and higher, you always also will get some problems, but then you should take the skimmer system. The data which you have in the mass spectrometer, I take here the data after 11.4 minutes and compared it within this database, and this fits good. So it's also possible to detect the substances, and this works without any problems, but I think also everybody will expect that it works. If we now go to inorganics, and with the inorganic, one other sample of organics, I took polystyrene, also with the same instrument, and what you can see is that you have the mass number 104, which is the mass number for the styrene, and you can also see in small traces the 208, which is could be the dimer of the styrene, and both have, so the 104 has 0.5 minutes, the 208 maybe a little bit later, but at the maximum, I would say at the same time, so no problem. And if you then go into the database and compare it, you see that you have at first hit the styrene, but there are still some other mass numbers in the higher region and also in the lower region. In the lower region at the middle, you see between the 78 and the 104, you see the 91. This comes probably from toluene. So this is a problem with the mass spectrometer. If you have several substances, it's sometimes hard to identify which substances are inside. And here it's also not, if I would use only the mass spectrometer, how could I be totally sure that the 91 is toluene and nothing else? But for the main products, it works in a lot of cases. But with polymers, if I would take polyethylene, for example, there are hundreds of substances which are involved, and then it becomes really, really hard to detect which substances are involved. But there we will come a little bit later to it. Now for the high temperature range, I took an example of one of my colleagues who measured lead telluride, and for sure you could think about which mass numbers could be important for the lead telluride, and there you must take the isotope tables and have a look which mass numbers could be there, and possibility is you add the mass number of lead and the mass number of the telluride, and then you get the mass number of your species. And if you want to think about the fraction, then you take the fraction of each isotope, make the multiplication to get the fraction of this molecule with this mass number. If you add all fractions together, then for sure you must have 1 or 100%, however you count it. And these are then mass numbers where you can think about which mass numbers to look into the MS or at the MS spectra. And here you see 4 pictures with always 2 mass numbers, with the 302 and 332, 333, and with all areas. And you see that some data are really flat, some others have a little bit less data points, so area detection has some errors, but the errors are not so big, because I compared the areas or the fractions by isotopes, and the mass number 336 was the highest fraction by isotopes, and I normalized the areas and the area of the 336 to the value, and then calculated the isotope fractions, which I found by the mass spectrometer, and there's an error of, let's say 5 to 6 to 7% maximum with the low values. So this is not bad, and as I have shown you with the carbon dioxide, this also works for inorganic materials with much higher mass number. And now I want to go to GCMS. So my first MS coupling I had bought in 1999, FTIR in 2003, and GCMS built up my own in 2005, I think, as far as I remember. So I've done a little bit also with GCMS. I was in an inorganic chair, so this was only some hobby for me, but I just got some samples from colleagues, and with the polymers I didn't had the good knowledge what could always happen and how to interpret my MS spectra, and then I decided to build my own GCMS coupling because I do not had the money. Otherwise I would have bought a good instrument, but in 2005 there was no commercial instrument also available. So GCMS. Here you see schematic or the picture of an STA coupled to an Agilent GCMS. The Agilent GCMS on the left side, and on the top of the GCMS there is a valve box, because to a GC you can't go or it makes no real sense to go over the whole time, so you add something with a valve or with a loop into the column, that there's a possibility of separation. But the first question is, why GCMS? So schematic part, also transfer line, the loop, then into the furnace of the GC, and then into the MSD. It's nothing new, everybody can do it in principle. Question is sometimes, how good are some things solved? And we use a valve system, and hopefully this video is running. Yes, you see with the valve system the blue part is filling the valve. This is coming from our TGA or STA and filling the content of the loop. And if you give now the order that the valve should move, then you see the carrier gas from the GC is going and take out the content of the loop and put it onto the column. So this is an easy, nice thing which works perfect with switching around, and you can fill and add whenever you want. But now again, why GCMS? Or the separation possibility. So we have a lot of substances which are evolved, and as I said, I always had a problem to identify them. Even with the FTIR and the MS coupled parallel, so with the use of the chromatography, your mixture is separated into several substances. And I want to show you with an easy experiment how good it is. And there I used solvents, ethanol and propanol, and in the ethanol there were 2% of butanone, so that I'm not allowed to drink the ethanol. And you see in the FTIR, hey, it could be possible to identify them. And what I have done was putting a small amount of this mixture into a crucible, heat the TG and analyzed it at the FTIR, and you see that I used different heating rates. So with the different heating rates and constants, you see different mass loss in the back from the TG curve, and in the front you see the increase of the FTIR spectra. And if we now take an FTIR spectra at some point, one comment here, this is also one possibility to calibrate your gas analyzer. So well known, if you know the amount of sample which is evolved and it's constant, then you can also calibrate your gas analyzer. And if we take now our spectra and the high concentrations, we can go into the database and search whether we found what it is. And the blue one is a different alcohol, and the pink one is the propanol, and we could identify the propanol. But the question is, if you would not know what it is, whether you are totally sure which alcohol you have. But if you know that one is propanol, it was no problem to identify the ethanol. And the rest, what is different from the red to the green, and green is the subtracted spectra in the FTIR, where I've subtracted the propanol. You see there some water because the solvent was not dry, and you see also small traces of carbon dioxide. But it's easy to identify, but I had no chance to find the butanol. And with the measurement in the GC, it was no problem. Ethanol, propanol, and butanol was well separated, and identification is easy. So that's why I like the GCMS for identifying of mixtures. If we now have a look what kind of possibilities or measuring modes we have with the GC. And we have 5, but the question is whether this 5 are real 5 or 3, so I talk about now of 3. One possibility is a quasi-continuous mode. So your TG run is running and you're switching the valve in time intervals, for example, every 2 minutes, and use the separation of the column at a high temperature. So separation is not the best, but you get a good overview what is evolved at different temperatures. So this is one possibility. Another possibility would be event control. And event control we are doing if you have a reaction rate which is bigger than whatever you define, your measurement, your heating stops, and you start your GC or you switch your valve. This is what you like to how you like to handle it. Normally switching the valve, keeping the column at low temperature, rising the temperature of the column, and then you have a better separation as if you would have the column always at the same temperature and higher temperature. So this is a normal GC run, but this takes for sure some time, and if you want to follow the reaction, you can't do it always like this, or you must have a fast GC, but they are not so common at the moment for the evolved gas analysis with TGAs. And the third one is working with a cryotrap. With a cryotrap, you always switch the valve, let's say every 1 minute, and gases which are not trapped in the valve, there you have the online information, and with the gases which are trapped in the valve after the last trapping or valve switching, you heat up the cryotrap and heat the GC oven, and then you have a normal GC run. So these are the 3 modes. If I want to take the 4th mode, then the event control, you can also do event control not by software with doing it at a special mass loss step. You can also say make an injection whenever you want. And the 5th method is, if you have a mass spectrometer, you can also take the mass spectrometer via a second valve as a normal mass spectrometer with a transfer line, so without the information of the chromatography. So these are the 5 principal modes. And looking at some examples, this is a measurement of the polystyrene, and you see the TG curve, and then in blue at the bottom you see the total ion current from the chromatogram, and then the mass number 104 and the mass number 208. And what you would think is, oh, the 208, the dimer is coming really, really late. And I can tell you this picture is wrong, because I have imported it via time. And normally with a TG, if you have a heating rate, it's independent whether you look by time or by temperature. But with chromatography, the dimer maybe took more time than the monomer, and the column temperature was only 180 degrees C. And there you see that the maximum in the tick is a little bit too late, but with our column and our gas flows which we use, we have the transfer path from the TG to the GC, and there via the column even nitrogen, which do not really make chromatography, needs more than 1 minute, so it must be late, and this is not corrected. And maybe this is also the problem, that the dimer needs longer time, and I have repeated the same measurement with the same amount of sample with a GC column temperature of 250 degrees C, and what you see is now that the dimer fits much, much closer to the monomer, so the separation via the column suggested you that you have the evolution later. It would be better to show it in a 3-dimensional way, because all what you inject at the same time needs different time on the column, but is the gas concentration and gas at this time. And we are working on this, but at the moment we only can show it 2-dimensional. And here is an extraction of the different valve switches. So you see here a sharp peak in the beginning, then a high peak which I cut a little bit, and then a broad peak in the middle, and then again a sharp small peak with a bigger peak, and this is the second injection. So it's a 2 minutes time difference. And what you can see in this quasi-continuous mode that you have at least one sharp peak in the beginning, one substance. The high peak has a shoulder, so this must be at least 2 and number 3. And the question is whether the broad signal is one or more different substances. You could for sure gamble a little bit with the temperature of the furnace, or you do an event control measurement. And in the event control, I showed you here the toluene, this in the beginning, then the styrene, and some other substances, and several with mass number 208 as the highest mass number, so several different dimers of the polystyrene. And you can also find some other substance if you have a higher concentration. And you see that I have to find some small peaks, do not have put what it is because I do not want to overload the slice. So this is possible with the event control. I'm nearly at the end of my talk, but I want to show you discuss some general things with evolved gas analysis and some general remarks. So imagine how you could influence your signal in the evolved gas analyzer. And for sure, with every gas analyzer, totally independent, whether you take an MS, an FTIR, a GCMS, or other gas analyzers which you couple to your thermoanalytical instrument, you can influence it by sample mass, by gas flow, and by heating rate. And as I said, I was a long time at university and teaching, and I'm always asking people, okay, what will happen with the peak area? And the peak area is related to the amount of evolved gas if I double the gas flow. Or what will happen if I double the sample mass? Or what will happen if I double the heating rate? Here I will stop for 30 seconds that you have some time to think about whether the area will be bigger, smaller, or stay the same, or whatever. Please think about for 30 seconds. I will drink something. Okay. Maybe you have an idea now what you expect, and I had the slides the first time on a seminar of quantification and asked the people. Some people were right, some people were wrong, so don't worry about this. And now with the double of gas flow. So with my normal gas flow, I had a peak area of 320, and then I doubled the gas flow, and the peak area was nearly the half. It's not exact the half. This could be due to several things. One possibility would be that my gas flow is not really, then other possibility would be that I do not have the same sample and there are some inhomogeneities, but it fits to be half of it like it should be. The third possibility, which is it in this case, is the linearity of the FTIR which I used was not as good for the carbon dioxide. So double of gas flow, half of amount of evolved gas concentration, so half of the area. If I double the amount of sample, for sure what you see here, the area is nearly doubled. So that's what everybody expects. That's things which you can deal. Now you know you can reduce your gas flow or increase your sample if you do not detect a material which you want to detect. And the third possibility is heating rate. With increasing of the heating rate, the air stays the same, because it's the same amount of evolved gas. Here we are in the time scale, and with a faster heating rate, this is the blue curve, the evolution is earlier. But the most important thing is that your signal-to-noise ratio becomes better. So the blue peak is higher than the red peak. The area is the same, so your detection limit. So now you know what you can do. Gas flow, sample amount, and heating rate to influence whether you will detect something, yes or no. And this is sometimes a problem. You have limitations of your detectors, whether you are in the ppm range or below. And with the gas flow, you have a bigger dilution. And then you must think about, can I detect this or this? And you must make your calculations. So that's where I'm at the end of my talk. So as a summary, I hoped that I could have shown you the unleashed power of gas analytic methods in the combination with thermal analyzers. That also every gas analyzer has its advantages and disadvantages, and evolved gas analysis is fascinating. It opens you a window in the characterization reaction studies, and I hope that I could have brought some of the fascination to you, that you, if you do not use it, use evolved gas analysis. If you do not have one and want to know whether a gas analyzer is suitable for your problem, best database in which I know in the net is from NIST Chemistry Webbook. If you want to see mass spectrum defragmentation and mass numbers, or FTIR, and whether you can detect things or we have an overlap, please go to NIST Webbook. Otherwise, you can also send me an email. Thank you all for your attention. So I'm finished now.
Okay, well, thank you for that presentation, and we do have a few questions from the attendees. So the first of those is, what is the typical sample size needed for FTIR versus MS versus GCMS requirements?
So this is one question is, what do you want to see? And normally with MS or FTIR coupling, I use samples in the region of 10 to 20 milligrams. If I do GCM measurements, I reduce the amount of sample to round about 1 milligram. There are several reasons. MS, no problem. If you have some dirt and the dirt stays in the capillary, you can cut the capillary. FTIR, if you have some dirt in your transfer path, it's easy to clean everything. With the GCMS and the Calumet, you have dirt and take a lot of sample, and some samples really produce really high boiling things, which makes chromatography on your transfer path, and the sensitivity of a GCMS is much higher than compared to the MS or the FTIR, because you had with the chromatography it's as a smaller part. It's not necessary to use high amounts. So that's why I use with GCMS always lower amounts. Does this answer this question?
Okay, thank you. Next, what sample injection loop sizes are available for the GCMS?
So we normally use a loop size of 250 microliters. This is standard, but for sure you can buy other loops or make your own loops in every size which you want to have. The problem is if you make the loop too big, and then you have a broad input on the column, and with a broad input to the column you have broad peaks, and you make separation lower, so you shouldn't increase it too high. And so we have the 250, and normally even on the injector of the GC we make a split from at least 10 to 1 or higher, because we do not need so much on the sample on the column.
Okay, thank you. Next question. Have you heard of TGA coupled with thermal desorption GCMS? If yes, can you please give us a simple introduction?
So this, my first GCMS coupling was thermal desorption, because this is the easiest way. What you should do is always, if you have a thermal desorber, you have a material in a tube, and let's say for organics, normally I would use Tenax, and you put it at the outlet of your TGA or STA, and then later take it to the thermal desorber, and the people who owns the GC and the thermal desorber stop to be your friends. Because if you take the whole amount of gas on the thermal desorber with all the dirt, you will see a lot of dirt afterwards in the GC. And when I started with this thermal desorber, I took around about 1 to 5% of the gas flow on the thermal desorber and small amount of sample. And I used old columns from the analytical people who thrown it away, and it was good enough for me in the beginning. So you should also, with the thermal desorber, you should make a split, that you do not get too much of dirt. And in a TGA or STA we produce a lot of dirt onto the absorber material, and then probably or hopefully your colleagues with the GCMS will be still your friends at the end.
Okay, thank you. Next question is it possible to detect and quantify fluorine-containing gases like hydrogen fluoride? The question says hydrogen fluorine. I assume.
So hydrogen HF. So HF, it should be possible. With the MS, you have sometimes the problem is the HF reacting with the transfer line. So with a quartz transfer line, it makes some reaction. If you have a steel transfer line, it should be possible to get it through it, or with a skimmer system. I know that a colleague of mine, Michael Feist, has made a publication of detection of and quantification of hydrogen fluoride with a skimmer system. With an FTIR, you see in the FTIR pretty well the hydrogen fluoride. What you must have a look is how big is the linear range, how to calibrate the FTIR, but it shouldn't be a problem. With columns, with the GCMS, I wouldn't do it. With the columns which I had used during my lifetime until now. So it's possible.
Okay, thank you. Can we use the MS as a sole instrument in the coupling STA-MS or skimmer STA-MS? I mean, in another experiment, to be connected directly to a thermal reactor without STA analysis.
So if you have the IALS, if you have a mass spectrometer with a transfer line system, this is totally easy to connect to every other instrument, and you can use it as a standalone. You must think a little bit about cold spots, but if you be aware of how to prevent the cold spot, it's no problem. Or sometimes it's no problem if you have a cold spot, because I also use some mass spectrometer even at room temperature in the connection, because if I only want to detect carbon monoxide, carbon dioxide, and things like this, it's not necessary that I heat the adapter. With a skimmer, I would say not so easy and more no. For sure, you can do things, and I also have done some things during my time at university, but not so easy. So with a transfer line system, yes.
Okay, thank you. It looks to me that if you're combining TGA with GCMS, then to line up the gas evolution in time with a GC oven run that you will already, sorry, the grammar is a little off here, that you will already know what your TGA will look like first. Do you have to characterize that a few times before coupling? Do you understand that question?
I
want me to read
hope
it
that I have understood it. So
okay.
It's not necessary to do a run before. So what I do if I got a sample and do a measurement here in the lab, what I normally do is I have normally some information about the sample. And then I choose round about 1 milligram. If I know a little bit about the sample, I make an injection every 2 minutes and to see what is happening during the evolution. So the quasi-continuous mode, and this is the first information which I have. If I then want to know more about the sample and have a better separation via the column, then I choose an injection at one point or at several points and make these measurements. Or I do a cryotrap if I'm only interested in the total thing, what is going out, and not to the time when it's going out. Because this is the same with thermodesorber. You lose this all time information because you're sampling the whole time in a thermodesorber tube. For sure, you can also change thermodesorber tubes, but most people don't do it. And so it's not necessary. So if I get a sample and you ask me, if I know a little bit about the sample, I make a plan and do a measurement and can give you good information. For best, I must do some measurements more. For some more measurements, sorry.
All right, thank you. What are the disadvantages of GCMS coupled to TGA?
Disadvantages.
Disadvantages.
Disadvantages. One disadvantage is if you have a really high